Hello and welcome to Golden Droplets episode number 20. I am transmitting this time from Colombia, Medellin, where I am in quarantine, waiting for my plane back home. Hopefully, I will fly tomorrow, the 20th. And in the meanwhile, while I am going to be talking about Excel and how to process geochemical data. For that, I will be using some geochemical results from the area that I was working here in Colombia, in Ibagué. The area belongs to sector resources, and I will be showing step by step how can you process your data. So, welcome again and be safe.
As I mentioned before, I was working in Colombia in the region of Ibagué for a company called Sector Resources. We were organizing the exploration plan and many other things, doing some QA/QC, etc. And as part of the work, we had some result of stream sediment, active stream sediment from the region, and I spent several days processing this data. And I thought it would be great if I can show you the sequence of events and how I use not only Excel, but also Weka, Rapidminer, compositional data analysis, Surfer, the whole package of software to get to my maps. So I will show you the whole sequence, and in a later episode, I will be going to details of how Weka works, how Rapidminer works, etc., etc., etc. The QR sign that you see here on your right is a direct link to my book of geochemical exploring geochemical data using Weka compositional analysis and insight, which is this book, and I strongly recommend you buy it. It's a step-by-step graphical guide of how to do all the things that you will see now in these videos and the next videos to come. First thing that I want to mention is that when this table and when you have your own data, you have your Excel table, save it as an XLSM that will allow you to use macros. Then just you can, and I would put to a table that contains this table of contents, which is very useful to have in your data, especially when you have so many tabs. We have 37 tabs, and using this table of content, you can just jump directly to one and then just go back if you need it. So this table of content is very useful. As I said, I will put a little Excel file, a link to a little Excel file that contains this table of content. And the only thing that you need to do is to go to that file, right click on the table of content, click on move or copy, and then you just select copy and you choose your book, and it will create this page automatically in your Excel. So I think I've mentioned before that the most important thing is that whatever is the format that you got your data, keep it. The original data as it was without any transformation, keep it, because you can always come back and redo whatever you did wrong. The next step will be to start doing some cleaning. And in my case, the cleaning was, get rid of all these columns that doesn't have information that I need. I just need the number of the sample, the parameters, and the coordinates. Talking about coordinates, I suggest you always do this little check, which is you create a new table and you just put all your coordinates there, and you select the two columns, some of these two columns. Okay, and then you go to insert and recommended charts. You click on recommended charts and you will see the chart here. Okay, so you click OK and obtain it. So the first time I did this, I obtained this graphic, and it's clearly that this sample down here has a problem with the coordinates. So if you look at the sample, you can see I put it here in red, it's missing a digit. So that is a very simple way. You just contact your people and say, please check the coordinates of sample 50, 44, 31. And you fix it, and that's it. If you don't have access, I mean, maybe this is all data, you just delete that sample, which is what I did. I just deleted the sample because we have plenty of samples to work with. Then I eliminated all the, as you see in the original table, there were a lot of values of zeros and minus. Zeros, minus, minus one. All this just means that it's below the detection limit or was not analyzed. I eliminated all that. One step that I didn't need to do, but usually is very important, is to convert all the elements to one unit. You usually receive from the lab results in percentage, part per million, and part per billion. Convert everything to part per million. I didn't need to do this because all the assays were on the same unit, part per million. The next step is amalgamation. And amalgamation, I'm talking basically about the rare earth element and the alkali. Sodium plus potassium, both elements are, they are alkali, so they can be joined together. And the rare earth element, these 12 elements, they all contain the same information. Very little variability. So for our studies, you can just add it all and have it all in one column called re. And most of the time when you're going to be applying machine learning and other techniques that I will be showing you, it will show that they don't carry enough important information for your work, so you can eliminate it. There are cases where both the sodium and potassium and the rare earth elements are very important. For example, when you're trying to define what is the most probable magmatic event, etc. In those cases, yes, you need to work with all the single element. You don't do the amalgamation. But one thing that you must always do is the normalization by manganese and iron. The thing is, especially manganese, when manganese forms, when it precipitates, it generates a redox very strong, and it forces many elements to precipitate, creating an anomaly that is not related to an ore body. It's a chemical uh, reaction. So it is recommended at least these elements here in this graphic to be normalized. Normalized means that you take the value of barium divided by the value of manganese, cobalt by manganese, zinc by manganese, etc. For the iron, you do the same with these elements here. And you will notice that for the Re, they are affected by both manganese and iron. So you divide the Re by the sum of manganese plus iron. And you have now your data normalized. Now you have here like 47 elements, most of which don't provide good information. Of course, there are methods like Rapidminer that we're going to see next, Weka, and even compositional data analysis that allows you to determine which elements contain the most variability, which are the most informative. But if you don't have access to any of those, like you are in the field and you don't have internet access, etc., there is a simple way of doing this thing, and it's just to determine the variability of your data. Variability is the standard deviation, the mean divided by the standard deviation and multiplied by 100. So anything that have a variability less than 150 to 200, you can eliminate. Just work with element that has high variability. The only exception, of course, is gold, because we cannot eliminate it. This is the element that we are looking for. Usually gold has a lot of variability because of the nugget effect. The fact that in this case it doesn't have that much variability is also an indication of the probable origin of this gold. Uh, we are in this area, we are talking about two possibilities: orogenic gold, I mean metamorphic source of the alteration of the amphibolites liberating the gold into the green schist, and also we have magmatic hydrothermal vein system with gold. Again, I'm just showing you the whole sequence. After this, you go and you open Rapidminer, and I will put a link down here so where you can download the Rapidminer software that you desktop software that you can install in your machine. Is free for 15 days, but I also will put a link to an online version that is free and you can use all the time. And the Rapidminer, what did I use it for in this case was to determine which elements were the most important. I got basically the same result as with my simple variability test. The next thing, very, very important, is to determine the erosional level of your data. You may have a very good geochemical anomaly on surface, and it may be the result of the erosion of a previously existing ore body. So just imagine that you have a body, and there are usually a series of elements that tend to form on top of the ore body. These are called supra-mineral elements. There are others that are formed below. They are called, of course, infra elements. There are techniques to determine specifically which ones are supra, which one are infra, but according to the chemical characteristic of this element, there are always such elements as silver, mercury, barium, zinc, that they form almost always on top of the deposit, while other elements like nickel, cobalt, chrome tend to form below. So if you make a coefficient of supra element by infra elements, if that coefficient has a value much bigger than 1, that means that the erosional level is right here and your body is down here. So you have an anomaly that coincides with an erosional level with a high number. That is a very perspective anomaly because it has not been eroded. You have a number that is very, very small, or sometimes even negative. That means that even if you have the anomaly there, it's just a residual anomaly because the erosional level is already at the bottom of your body, and you will not lose time exploring for those anomalies. This is a very useful technique. It's a Russian method. I am really astonished that it is not taught at the university because it's a very simple way to discriminate your anomalies in the field. So the way of doing this thing is very simple. You just select the elements, you select the average and the standard deviation for each of them, and then you go and create a new column where you standardize each value by the mean and the standard average, and then you sum all these values. And I suggest you put the formula integral part, so you will only get the one digit. Then you just plot this column on a map, and you will define which area has been completely eroded and you don't need to work there. Weka is for my money, because it's free, is the best system for machine learning in the world. It's an open source, it's completely free. I will put a link also in the down here for where you can download it. It was created by a Canadian that works at the Waikato, New Zealand University. And if you go to YouTube, you will find a lot of videos of him explaining the system. The problem is that he's explaining the system in a very general way, not as a geologist. So that is why I always recommend you to click here and to get my book, because in my book we go step by step and specifically oriented to geology. I'm just explaining a little bit now. Weka uses a classifying method. I mean, it will make deductions of your data, but he needs to know which is the element that you want to test. In our case, it's gold, but it doesn't work directly with a number. You need to convert the values of gold into categories. And one simple way of doing this thing is you just take the column of gold and you find out what is the, for example, the second quartile and the third quartile. And then you put an equation saying if my gold value is bigger than the third quartile, that would be a high. If it is bigger than the second quartile, it will be a medium, else it will be a low. And then you create your table of high, medium, etc. As I said, I will be showing the results and how to work with Weka on the next video. So this is what we did with Weka. We selected elements, we did histograms, we used classifiers. And this is the part that I really like, the tree view, is the classification. And I must say that I have been working with statistics for over 20 years or more. And the results that you get by applying machine learning, it is almost impossible to get by just applying statistics. This is something really useful, and I encourage everybody to start using machine learning today. You don't need Watson, you don't need big data, you only need Weka or Rapidminer, one of the two. But these kind of tables are really, really interesting because in this case, for example, let's say that you're constrained in your budget, which is everybody's constrained their budget, and you decide, okay, I'm going to do first multi-element analysis, and if, for example, the value of silver is very high, then I will send those samples to do fire assays, which is a way of doing it. But with this tree table, you can say, okay, I'll do first my multi-element analysis. And if I am interested in getting the high values, what I need to do is to send for fire assay the sample that have more than 638 part of manganese, more than 205 vanadium, and then chrome between 165 and 102. And that is a sample with high value. Now, if you go this way, you get the aluminum also in a range. So you have two high samples, and this is because at the area where we're working, there are two types of gold. One hydrothermally related to intrusive, and one orogenic. And the way we know this is because the orogenic will have the influence by the major oxides. Of course, I'm doing a little bit of advertising for good friends of mine from Activation Laboratory. They have now a method called Ultra Trace UT1, which include all the multi-element plus gold, semi-quantitative gold, but you know, is a good way. Anyway, this table will help you think about the geology of your deposit, not only to select which elements you will send for further analysis. There's there are some three-dimensional this construction that you can do, and I will explain this later, but it's beautiful to see how the values go from the low values in amphibolites to the high values in the green schist, which is a characteristic of an orogenic type of deposit. Now, We also will be using compositional data analysis. Again, there will be a link to download CodaPack. CodaPack is a free software, and this is not a good to have. This is a necessity. Even the guy that invented correlation, Pearson, wrote that his method, will not work with closed data. And closed data are data that are estimated or on the basis of a total, for example, part per million, part per trillion, or percentage. Everything that is estimated over a general sum, that is what is called a closed data. And this is something that is being known since ever. But correlation, especially correlation analysis, is so useful that geologists will use it even knowing that, yes, there will be problems, but I will get the best correlations. And I have a I have written in a book about this, why and how should geologists use compositional data analysis. I will also put a link to, to this book, which explains in detail why we need to use compositional data analysis. There was an English scientist called Atkinson, solved the problem by creating a statistics for the closed environments called the simplex. And not only that, he created statistics that can work in the closed system, but he also found a way of opening the data, like imagine a sphere and you project it into a plane. So he found a way of doing this. It's called the LR. And, and then a group of Spanish from the University of Catalonia, I think, uh, I will check, they continue the development of the method, and they have two more ways of opening the data, the CLR and the ILR. Again, I will explain all this in detail upcoming episode, but the most important thing here is two things. First, organize the data as you see in this table. This is based on the enzyme leach technique, where each type of deposit has a series of elements that are characteristic for them. So when we're going to be doing maps, we're going to be doing a map of gold or mercury. No, we're going to be doing a map of the oxidation suite, which is basically precious metal. We're not going to be doing a map of cobalt or lead or zinc. We're going to be doing a map for base metals, etc. Then we reduce the amount of elements. While CoDa can work with missing data, I prefer not to give him missing data, especially if I eliminate all the blanks and I have more than 30 samples, that would be perfect. So I prefer to eliminate, don't give the system blank data, give me a full data set. The other thing that the compositional data analysis cannot work with zeros. So if you have zeros, you need to eliminate it. And the last thing that you need to do before starting to work with compositional data analysis is to add a column at the end, which is the rest. And this is simply 100 less the sum of all the other elements. Usually that number is near 98, 99. The reason why here is so low is because this lab gave silica. So we have all the values of silica here. So that's why we get the rest like values, not 90s, but 50s, etc. Next, I will show you the result of applying in compositional data analysis. You can have your classical statistics, you know, normal, the mean, the standard deviation, the quartiles, etc. But you can also have your statistic in the simplex, in the closed system. And the statistic, the way I define this thing is that normal statistics is numbers. When you're talking about compositional data analysis, you're talking about distribution in space. It's a graphical statistics, not a numerical statistic. But one of the things that the program gives you when you're working in the simplex, in the closed data, it gives you this variation array. And in red, there are the elements that have the most important information. So you can see the stronger the red, the most information. The blue means that they don't have much information. So you can select using this table which elements you will be working. This is another way of doing the thing. The program also does a thing called the atypicality test, which is an amazing technique. It takes each sample and compares all the elements with every other samples in your data set. And it will select which samples are atypical, are out of the general population. These are the ones that are marked here in reds, the 7, the 8, the 15, the 17. If you just then take the coordinates of this sample, you plot it on the map, you're gonna get points of interest. And usually, like almost all the time, these points of interest are related to zone of mineralization or lixiviation. They are really outside the normal range of data. Another interesting plot is the CLR plot. And I was telling you a minute ago that statistic in the composition of data analysis is graphical. So there are rules to interpret these things. Like, for example, elements that are close together contain more or less the same information. So you don't need to use them. The longer the axis, the more strong is the information. And when you want to do a ternary diagram, for example, you take a couple of elements that are together and compared to one that is completely opposite to it. So, for example, I get gold molybdenum and I compare to nickel. So you will start getting here association of elements that you will test later in a graphical way. Another thing that the program does when it gives you the component analysis, and then you just select how many components are interesting. As this case, 9 was the amount of coordinates, and then you start exploring. And again, I'm going to do this later. I'm just going to show you basically quickly. You just click on the element and you organize them from maximum to minimum, and you can see that you have here very good factor analysis for gold, very strong. Gold, copper, niobium, mercury, and then divided by sodium and cesium. And again, if you go back to the triangle, you will see those elements represented here. Based on the analysis of this 7-factor analysis, we get this combination of elements, which are clearly, one is orogenic and the other two are related to the magmatic event. Compositional data analysis is not only processing data, it forces you to think about the geology. So it's much better for interpretation. There are other principal component analysis. You can also do dendrograms, and you can do transpose dendrogram, where you can, what you do is just determining not the element, but the samples. Which samples are groups of thing. And again, we get here two big blocks. One is the orogenic, and the other one is the porphyritic. As I mentioned, the program will do 3 types of classifications: ALR, CLR, and ILR. Again, I will explain that later. But once you have your data transformed, then you can use your normal statistics methods without any problem, like correlations. And in the case of correlation, you get all this huge table. But the thing we are interested in gold, one thing that I do, I just copy the column of gold and just paste it and click from maximum to minimum. And it selects me which elements are important in this thing. So for this case, I got what I call the range correlation coefficient of gold plus silica divided by aluminum. Again, major elements that most probably is an orogenic. You can also do factor analysis. And the factor analysis is the same thing. It's like it gives you a principal component, like principal component analysis. You just select it and you organize it from top to bottom. And you see here you have a gold niobium divided by magnesium, aluminum, chrome, and magnesium. Okay, and that's the factor that you will use. CLR is the same. You can get the correlations, you can get the factor. And then we have the ILR. ILR is so important because this is the only method that I know where you can introduce geological information into the processing of the data. And instead of getting results of different elements, you get results of potential mineralogical associations. So you got here a column for the precious metal, the base metal calcophyll, high field strength element, rare earth element, lithological anomalies, and major oxides. Because this is so important, I will give a lot of time and I will show you practically how you do this in compositional data analysis, because this is one of the most useful technique that I know. And again, you can do a factor analysis, and that is a factor analysis that you got. When you get all this, then I use Surfer for my graphical presentation. I don't know what you use, but all these methods are basically the same. You have coordinates and then you have the parameters. Here I just have the coordinates, and then I put here all the coefficients, the different coefficients that I got from applying, you know, composition data analysis, Rapidminer, Weka, all these coefficients. And I will obtain maps for each one of them. In this case, we have a series of these parameters that are characteristic for the orogenic type of mineralization, and others that are characteristic for the magmatic type of mineralization. And one way of doing an additive anomaly, like combining all these things into just one map, is by a technique that I have developed. I call it the quartile technique, and it's basically very simple. Let me show you. You have, for example, here, this is the quartile for the orogenic type. So these are the parameters, the AOE3, the RCC1. These all are equations that will map the orogenic type of deposit. Okay, so what you do is you just determine the third quartile of each of them, and then down here you copy again the formula, but then you put this equation. If the original value is bigger than the third quartile, then you will put a value of 5. If not, you put a value of 0. Okay, so here is 0, 0, 0, and then here is 5, and there's 0. The next column will be the sum of all the quartiles. In this case, is 5 because all the other were 0. But then you have the most important one. It's called the perspectivity, which is in this case 20. How do we get to that value? It's very simple. If this sample has 5 on all these parameters, it will be 5, 10, 15, 20, 25. I only have 5. So you have, if I divide 5 by 25, I get 20. Here I get 0 because none of the samples were interesting. But down here I get 60 because one sample, 2 parameters of the samples were 5 and the other ones were 0. So the perspectivity map is a map from 0 to 100%, how sure you are that that anomaly corresponds to an orogenic type of deposit. So that is what I put here in Surfer, the quartile for orogenic, the quartile for igneous, and a total quartile where I just didn't discriminate between orogenic and magmatic. So I think this has been a very long explanation, and I will show the maps result later. Probably next episode, I will start showing you the different section of this table, which is, as I mentioned, Weka, then Rapidminer, then Weka, and then compositional data analysis. It will probably take a couple of episodes more. And at the end, I will show you the maps and how we use Surfer, the variograms, and all these things to do beautiful and very useful maps. Well, that will be all. Well, that was all for today. It was a long episode and a lot to learn and to discuss. I assume that you will be reviewing this episode many times. I strongly recommend that you use your data and follow the examples here and do all this transformation. Wishing you all health. Let's hope that this coronavirus will end soon. Have a great day and see you on episode number 21. Have a nice day.